So the last talk before the coffee break is by Daniele Ielmini, Neuromorphic Computing with volatile memristors and memtransistors. So we are going back to engineering here.
Thank you for the introduction. Okay. Thank you. So my name is Daniele Ielmini. Morning, everyone. And my title today is Neuromorphic Computing with volatile memristors and 2D semiconductors. So this talk is about hardware. So I'm going to try to show some examples of how we use in our lab. We use memory devices or memristors to actually compute, similar to the brain. And the main motivation around this, behind this work and behind much of the work that we do in our lab in Milan is the sustainability, energy sustainability of computing. So this has been mentioned several times, including this morning, but the previous talk. We know, especially generative AI, currently we are pretty familiar with ChatGPT and other generative AI concepts. It's very nice, very useful. It's going to be a revolution for our society and information, but at the same time, it's scary how much energy these generative AI concepts use for the training, for the inference. And this has been mentioned and pointed out several times. The carbon footprint for this type of AI is really unsustainable. So we need to figure out something else. Okay, so I think the problem with this generative AI is both from a software algorithm level and a hardware level. From the software level, my feeling is that these generative AI are really super functional, super efficient, super accurate, but at the same time, they are probably too much redundant. They require too many computation, lots of matrix vector multiplication, lots of matrix multiplication, and this is probably an overkill with respect to the target. On the hardware side, that is where we are more expert in my group. On the hardware side, it has been mentioned several times that the problem lies with the von Neumann architecture. So we know that for computing, generally we have a processing unit here that is very efficient in running extensive computation. But the problem is that especially with data-intensive computing, all of these data and parameters that are needed for the computation are sitting in a memory. And the memory is sitting on a different chip. Okay, so we have this chip-to-chip connection, and every time the processing unit needs to compute something, there is a lot of data movement going back and forth between the memory and the processing unit. And this data access, this memory access, is what is really impacting the energy consumption and the latency. So we have a data movement issue, we have a memory bottleneck issue. This has been mentioned several times, and everybody knows that this is the main problem. But the fact is that the digital conventional computing systems are based on this von Neumann architecture. And what you can do is probably to improve this memory bottleneck. So if you look at the GPU architecture nowadays, the GPU is the standard hardware to run, for instance, this generative AI training and inference. There is a so-called high bandwidth memory, and this high bandwidth memory is very parallelly connected to the processing unit, and the structure is such that there is an optimization and maximization of the connection between the memory and the processing unit. But from a revolutionary or radically, if you want to radically solve this problem, then we need to look at the brain. And the brain is, of course, totally different. There is no von Neumann architecture in the brain. And the structure of the neurobiological network is such that we have neurons, we have synapses, we have dendrites, we have all the building blocks. They all have some function, but there is no real memory or real computing unit. Everything is mixed together in some very optimized way, and probably not very clear still today how these compute and memory operations and building blocks are organized, actually. So we need to take inspiration from the brain, and this is the main concept that has been mentioned several times in memory computing. Try to compute within the memory. So instead of compute-centric architecture, try to do some kind of data-centric computing, where the memory is the center, the core of the computation. We compute within the memory, we compute within the data, literally, and try to minimize as much as possible or even suppress any data movement, and try to also take advantage of the large parallelism that is available within the memory unit, because the memory unit is very modular, is very regular with rows and columns, and it allows for much very high parallelism. So this is the main concept, main motivation. Now the question is how we really take advantage of the memory and how we try to take inspiration from the brain. So if you look at the brain, as I mentioned, here, this is a very simplistic description that we have of some neurons connected all together through axons, dendrites, and synapses, and through spikes. Okay, so they interact by sending spikes to one to the other, and actually, every building block here has some specific function, and our purpose is to try to take inspiration from this example, this paradigm, and to try to figure out ways of how to translate these functions into some device. Okay, so the idea here is that we take one device, and this device is gonna replicate or emulate artificially the function that we see in the biological system. For instance, here we have a soma. One of the model for the soma is that it's basically collecting several spikes after waiting by the synapses. And so this is one example how we electrical engineer replicate this type of summation of products, basically. This is a cross-point array. We apply some voltage signal here and across the columns, and these signals will be weighted by the conductances, which are embodied by this memory element, and then we are going to collect the current. And the collection of the current through Kirchhoff's law will be summation, and the multiplication by voltage and conductance will actually be the multiplication. So this is a way to emulate. Of course, this is not literally accurate, but this is a way to model in hardware what we see in the brain. Second example, the soma is actually, instead of looking at this, replicating this kind of static summation of the current, we can also integrate the currents. And this is the so-called integrate and fire model. And this integrate and fire can be replicated by individual memory elements. This has been shown several times using resistive switching memory or ARM or phase change memory. For instance, you can apply several spikes to a phase change memory. This will heat up the material locally at the nanoscale, change the crystalline fraction, increase the crystalline fraction, change the conductivity, and through that change of the conductivity, you can also change the voltage, like the membrane voltage or current or some other physical electrical parameter. Dendrite. So yesterday we've heard this great talk by Professor Boahen, and he was suggesting that actually the dendrite are capable of this sequence recognition. And this sequence recognition can be, for instance, replicated by this series connection of ferroelectric FET devices, where the order of the excitation dictates the functionality. And synapses are probably the most intriguing aspect, because many people believe that the synapses are actually the real location for the memory. And synapses are the place where the long-term synaptic plasticity takes place. For instance, one example, a very popular example, is the STDP, the spike time independent plasticity. These can be replicated in several memory devices, such as resistive switching memory and phase change memory. and short-term synaptic excitation. So this is a different behavior of the synapse, which is also called EPSC, excitatory postsynaptic current, where the excitation of the synapse actually leads to some temporary and transient excitation of the connection. That is responsible for the short-term memory that is very useful for our behaviors. For instance, now if you listen to my talk and you're understanding what I say, this is because of the short-term memory taking place in your brain. So now in my talk, I'm gonna actually focus on the very last of these examples, okay, the short-term memory, and I will show you a couple of examples of two devices that actually display this kind of short-term memory and how we can use this short-term memory to replicate some function of the human brain. And the two examples in hardware are the first one is the volatile resistive switching memory. So resistive switching memory is basically a two-terminal device where you can switch the device in the on state from the off state, and then it's gonna spontaneously decay back to the off state. Second example is a 2D semiconductor, here also called memtransistor. Some people call it memtransistor because it's a three-terminal device, such as a transistor, but it's also memristive. It shows a memristive behavior. In this case, I'm going to discuss the physical mechanism for this memtransistive behavior. It's a charge trap-based behavior, and I'm going to show you how we can use this device for reservoir computing. Okay, so let me move to the outline for this stuff. So first of all, as I mentioned, volatile are RAM for time and frequency computation. Second topic is the molybdenum sulfide charge trap memory for reservoir computing. So let me start first with this volatile RAM. Volatile RAM, I guess many of you might be familiar, especially the memristive community is familiar with this concept. It's a two-terminal device. We have a hafnium oxide, for instance, or any oxide, metal oxide typically, layer embedded into two metallic electrodes. The top electrode in this case is silver for a special reason, because the silver will induce this metallic filament during switching, and this metallic filament will be unstable. So as you apply some voltage, which is also shown here, if you apply some voltage, if you reach a critical voltage called the set voltage transition, which is 0.3 volt in this case, you're gonna see a steep transition from off state to on state, which means that the device is basically an insulator, initially an insulator, and then suddenly starts to conduct current. And actually, this current here is minimized. It is controlled to a certain compliance level, which is around 1 or few microamp, thanks to the presence of this transistor. This select transistor is just there for the purpose of selecting or unselecting the device and fixing the maximum current during the set transition. Otherwise, this set transition might eventually induce some irreversible breakdown of the device. Then if you reduce the voltage back to 0, at some point you're gonna see that the current spontaneously drops back to the off state. Okay, so this device cannot remain in the on state permanently, opposite to other RAM, non-volatile memory technology, because the silver filament actually is unstable. There is a thermodynamic tendency to minimize the surface to volume ratio. So this filament has excessive surface, too much energy, and it wants to go back to the a more spherical size or shape that will minimize the thermodynamic energy. So this is what actually takes place from a more detailed nano scale point of view. So this shows, for instance, one experiment where we applied a spike, a voltage spike, just to stimulate the formation of a filament, and then we monitor in time the current response. So we see that the device is actually switching on to some few microamp, in this case, 10 microamp. And then after the spike, the device remains in the on state. Okay, there was a very small applied voltage just to monitor the state of the device. And then after some time, the current drops to 0. And this shows that there is a retention time of about 300 microseconds in this case. And this is the retention time for the device, the time the filament can survive within the device. And then you're gonna see that this retention time can change. It can be shorter than 300 microseconds, can be even longer. It can reach also millisecond or second scale. It depends a lot on the structure and how you program the device and what is the current, the programming current. But then the explanation for this spontaneous decay or collapse of the device is, as I mentioned, the fact that the thermodynamic energy is minimized by reducing as much as possible the surface to volume ratio. So the linear filament will become a spherical dot or a droplet kind of shape. And this is very nicely demonstrated by in situ experiments, as you can see here, where people have actually looked at what happens during the switching of one of these devices. And you can maybe quite clearly see that from an elongated filamentary shape, the filament tends to collapse into droplets. Okay, so now that we understand how the hardware really works, you're going to recognize a similarity with the short-term memory effect in the synapse. So in the synapse, what happens is that very similar to what I have shown here, there is an electrical stimulation that reaches the presynaptic terminal of this synapse, and this will result in a release of a neurotransmitter. This neurotransmitter is then released and collected at the receptor side, and this will open as a key, pretty much. It will open the ionic channel. The ionic channel, in turn, will result in the inlet of calcium ions into the post-terminal, post-synaptic terminal here. So calcium and sodium ions will be let into the postsynaptic terminal, and this will result in an increase of the potential, membrane potential, and eventually it will approach the threshold for fire. This is one example how the glutamate signal will induce the ionic channel opening, and you can see that in a matter of around 1 second, the ionic channel will close eventually, okay? Opening, and then because of this short-term memory, the ionic channel will close spontaneously. This short-term memory actually turns out it's a very important aspect for sensing, adaptation, information processing in our brain. So it's very important that we try to have this device or some kind of similar device, like the volatile RAM, that is capable of replicating this short-term memory without complicated CMOS transistor with capacitors or inductors or some other complicated shape. This is just one nanoscale device that can replicate this relatively long constant time. So what can we use this device for? One example is, this spatial temporal recognition, where we can recognize a sequence. So in this case, I'm going to focus on a very simple example of 2 spikes. Okay, you have 2 spikes, A and B, and you want to recognize what's the sequence, either a preferred sequence A followed by B, or a non-preferred sequence B followed by A. So as soon that you have this structure here, you have 2 branches. Okay, so the spike A is applied to the first synapse here. There is consists of several of these volatile RAM devices that I showed you. We are using several of, not just one, because just one will result in a too much stochastic dispersion or spread of the retention time. Because in fact, one of the aspect of this retention time is the large stochastic behavior. So we want to minimize this stochastic behavior and also enable something like an exponential shape of this decay of the current. So we put many of them, so just 3 in this case, but ideally we can also put 10 or more, and this will serve as a excitatory synapse. And then we have a second branch where we apply the spike B, and this is going to be the inhibitory branch. And these 2 currents will eventually be connected in this subtraction node here, and we compute the current as a subtraction of these IA minus IB. So what happens if we apply spike A followed by spike B? In this case, is that we have the overall current here, the EPSC, which is excitatory postsynaptic current, is going to consist of just one spike, one positive spike, because A is followed by B, so if you subtract these two exponential, almost exponential shapes of the current, you're going to have a positive spike. Instead, if you apply a non-preferred sequence, B followed by A, then the spike will be negative. Okay, because the B, the inhibitory current is just slightly before the excitatory current. So then what you do is quite easy now to discriminate between the AB followed or BA, because now in one case the current will be positive, the other case the current will be negative. If you compare the current to a threshold like 3 microamp in this case, and here you can see the histogram. So the currents in the case of A, B, and BA sequence is very easy to discriminate between the two different sequences. So this is a very simple example how you can discriminate between these two sequences. Now you can extend this concept to the direction selectivity function in the retina. So what happens in the retina is that the photoreceptors are actually connected to some excitatory synapses and inhibitory synapses, which are blue and yellow in this case, and they are covering separate regions. Okay, so in this case, for instance, you have on the left you have the excitatory synapses, and on the right you have the inhibitory synapses. So, and these are connected to the direction selective ganglion cell. So this ganglion cell is basically collecting the currents from these synapses and comparing the spike response from the excitatory and the inhibitory. And what we can do here is very similar to the previous case. We mimic the excitatory and inhibitory synapses by the volatile synapses in the excitatory branch and inhibitory branch, and we subtract the two currents so that when, for instance, if there is an image moving across the photoreceptor from the left to right, then this image will first excite the excitatory synapses and then the inhibitory synapses. And as a result, this will result in a preferred sequence, A followed by B. And we can discriminate this preferred sequence by just looking at the sign of the EPSC. And on the other hand, if the direction is the opposite, from right to left, then in that case, the sign will be negative. EPSC will have negative current. And in this case, you can discriminate between the 0 degree of the direction, which means from left to right, and 180, which means from right to left. And if this bar is instead moving not horizontally but vertically, then this system is not capable, of course, of detecting the direction. So what you can do is to upgrade this system to by taking inspiration from this turbust amacrine cell, or SAC. This is actually a structure that we have in the retina and consists of 4 different regions. So instead of only 2, you have 4 regions, each one consisting of 2 synapses, the excitatory and inhibitory synapses. Inhibitory will be in the center, excitatory will be all around. And now you have 4 different regions, and all these 4 different regions will be connected to the direction selective ganglion cell. So in this case, it's easy to understand that if you have something moving from left to right, then the east side, which is here, is going to respond with a positive spike. The west side will respond with a negative spike, as shown here, and the south and north will just not respond because there is no temporal sequence of the excitation of excitatory and inhibitory. On the opposite case, if the bar is moving from right to left, then you will have a positive peak on the west side, negative peak on the east side. And if something is moving vertically, now you will see the south with a positive response, and the north with a negative peak, and so on. So in this case, by looking at the output of these 4 different regions, you can easily recognize the direction of this of the object. So this is just one example how with the volatile RN device you can actually detect the sequence of the time events and also extend this for direction selectivity in the human retina. And this work actually was done by Wei Wang, which was a few years ago my postdoc in my group. Then let's move on to a same device, but now I'm going to show you a slightly different approach. Here we are using this device for detecting the frequency. So here we are applying a train of spikes here, and this train of spike will be applied to this device. So what happens is that if the frequency is, if the voltage is relatively low, then this device will switch on after a few spikes. So you need to insist, okay, with several spikes until you eventually achieve and make it to switch on your device. If the voltage increases instead, the time for switching decreases. Like in the first case, you need 21 milliseconds, in the second case, 8 milliseconds. And if you further increase the voltage, then in 2 milliseconds, the device will switch on. Okay, and this is just a probabilistic probability of switching of this device, where the probability for switching increases from 0 to 1 as the voltage increases. And actually, if you increase the frequency, then the probability also increases, because this is the probability for switching within a given amount of time. So the larger the frequency, the larger the number of pulses, so the larger the probability for the switching. Now we have applied this concept to several synapses, several devices, which are connected in parallel, as shown here. And each of these devices is stimulated by a different voltage. So the same frequency, the same pulses, but different amplitude. So what happens here is that if the frequency is relatively low, so only one device, the one with the larger voltage, which is, I guess, probably this one, okay? So only the device stimulated with a larger frequency will make it to switch. Okay, and in fact, you can see these spikes. After some time, these spikes will signal that actually one device is on. But if I increase the frequency, then also the second device, because the probability now for switching is larger, now also the second device, despite the voltage is smaller, this device will also switch on. So instead of just one device on, I'm going to see 2 devices on. And the current is twice, because the current is the same for each device, and if the one device is on or 2 devices are on, I'm going to see it from the current, from the level of the current. And then if I further increase the frequency, then all 3 devices will eventually switch on, and I will see that it from the current. So now if I look at the probability for how many devices are on, okay, the number of devices that are on as a function of the frequency, I find a very, very interesting property that the number of on devices actually increases with the log of the frequency. And this is because the probability for switching is actually an exponential function of voltage. So now this log frequency scale is very crucial, because if you look at the cochlea, which is one organ that we have in your ear, this is also the case for the cochlea, where the so-called cochlear depth depends on exponentially, or depends on the log of the frequency here. So what is the cochlea? I'm not an expert, but I'm gonna just very quickly give you some hint of what is the cochlea. Here, this is the so-called cochlea, which in Latin means a snail. So in fact, this is a snail shape where we have a channel for the sound waves to propagate, and in this channel we have cilia, and these cilia are basically very small filaments that can be stiffer or less stiff or more softer, and depending on the stiffness, they are sensitive to high frequency. For instance, at this side, they're going to be sensitive to high frequency, close to the ultrasound. And as you move deeper into the cochlea, they will be sensitive to lower and lower frequency. So based on the depth of this excitation in the cochlea, then we can recognize all the different frequencies. And we can listen to music, and we can appreciate the music, and so on. So, and this shows what happens as a function of for different depth within the cochlea, what is the frequency sensitivity. And you can see that the frequency scale is log scale, and you can see that at each depth, at each position along the cochlea, you're gonna find a different peak, a different position of the peak. So this is very similar to what I shown before using these volatile RN devices. Here we basically connected these devices all being stimulated with the same frequency of the same spike, but with a different voltage, and each of those are connected to one XOR output. The XOR output is basically making sure to position the exact boundary between the on devices and the off devices, so that basically we expect just one single output to be on of these XOR gates, and this will mark basically the frequency, because this will mark the boundary between the on devices and the off devices. In fact, here you can see the position of this XOR output as a function of the log of the frequency, and you can see the linear dependence of the position versus the log of frequency. So this is called tonotopic mapping, if you look at the literature, and basically this is tono in Greek means frequency, and topic or topos means place. So it is a translation from frequency to space. And this can be done easily with using these volatile RN devices. And this work was done by my former PhD student, Alessandro Milozzi, who is also passionate of music. And he actually tried to process, using this hardware, the Ode to Joy by Beethoven, and he was capable of showing this tonotopic mapping of this very famous piece of music in hardware. Okay, let me switch very quickly to the second topic of my talk, which is the reservoir computing with 2D semiconductors. So here, as I mentioned, we have a 2D semiconductor. In this case, it is a molybdenum sulfide, which is a 2D materials, meaning that it is capable of standing pretty much as graphene on a molecular or atomic thickness. And in this case, this is not a monolayer, this is a few layer channel. We exfoliated this channel on a silicon oxide surface and with a positive source and drain, and this device pretty much behaves as a transistor. You can see the transistor characteristics here showing subthreshold behavior and the large hysteresis. This large hysteresis is because of the charge trapping taking place at the interface between the 2D semiconductor and the silicon oxide. So what happens is that if you apply a relatively large voltage, gate voltage in this case, this will induce a filling of the traps here by negative electrons, and this will result in a shift of the threshold voltage to larger voltage. And on the other hand, if you apply negative voltage, this will empty the traps, and this will result in a lowering of the threshold voltage. So this is responsible for this hysteresis, but this is also very nice and can be used as a memory. Okay, this is short-term memory. Once again, the retention time is in the range of a few seconds, and so you can exploit this short-term memory in a kind of short-term plasticity or short-term potentiation effect, as shown here. So here in this case, we're applying gate pulses. Negative pulses to the device, to the gate of the device, measuring the current, and the current will show an increase, gradual increase of the current. And this is summarized here because of you are applying a negative voltage, this will result in emptying of the traps and lowering of the threshold voltage, so that if you probe the current at a given gate voltage, this current will actually increase. As the threshold voltage decreases, the current increases. But the beauty of this device is that actually you can probe the current in the subthreshold domain. And so this is very effective to reduce the current, because now, as you can see here, we are in the range of picoamp, nanoamp, or few nanoamp, which is very effective in reducing the current and reducing the power consumption. So this shows some experiments where we applied a train of pulses to this device at different read voltages, and you can see this potentiation in the range of tens of nanosiemens. We can also actually apply the same signal, similar signal, to the drain side. Okay, is not the same, but actually can be even better in terms of linearity, because in fact you can see here the potentiation of the conductance in this case is much more linear, and actually this appears to be one of the best in class in terms of the linearity of this synaptic behavior compared to other devices. Then, as I mentioned, this is a short-term memory, which means that after you apply the train of pulses, then the device will spontaneously decay because of the spontaneous detrapping of electrons from the interface states. And the retention time is in the range of few seconds, as shown here. So now we can use this potentiation and depression effect as a nonlinear response, which is capable of spatiotemporal signal recognition. And this goes by the name of reservoir computing. That I show you one example here of this reservoir computing. So basically, assume that you have an image, okay, like this. This is a very simple image showing a 7, okay? And this 7 is, instead of a static frame, assume that you actually submit this 7 in time, okay? So each time each time you submit a certain column, and this column is gonna stimulate a column of these reservoir computing devices, these charge trap memory devices. So for instance, the first device on the top row here will receive 4 spikes in a row, and this will result in a continuous potentiation of the device, as shown here. But the other device here will just receive just 1 pulse at the beginning, which is shown here in yellow, and then 0, 0, 0. So this device will be potentiated at time 0 and then receive nothing, and then spontaneously decay back to 0. And all devices will, the final state of the devices will depend on how many pulses and when the pulses were applied. So it is, thanks to this nonlinearity, this system is capable of extracting the feature and recognizing this spatiotemporal pattern. Here you see some example of all different sequences that you can apply from 0000 to 1111, all different sequences, and in reality, all this final state will actually be related to the sequence, the time-dependent sequence that have been applied. So you can apply this to all different images, as shown before, not only 7, but the 1, the 2, the 3, and so on. And each of these pattern will actually show a different shape, a different feature, and can be easily recognized by this concept. So this is, of course, a toy problem, just to show the basic function, but we want to apply this concept to some more significant signal, which is in this case electrophysiological signal. So for instance, assume that you take some signal from the brain. It might be a low field potential from MEA, or electroencephalography, electromyography from muscles, for instance, electrocardiogram, and so on. So you have this signal, you apply this signal after proper signal preconditioning, like filtering, amplification, and so on, to our devices, which is charge trap memory devices, which is the so-called reservoir layer. And then the output of this reservoir layer can be also post-processed by so-called readout network, or even a very simple digital processing, like even a simple threshold, or KNN, K nearest neighbor, or decision tree, or something like that. So this is the concept basically, and so to prove this concept, we have first apply random signals. Okay, so these are not really electrophysiological signals, but just random signals that were synthetically, artificially generated and applied to our device, and our device indeed showed potentiation as shown here, and we measured each and every change of the conductance, delta G, after each of these pulses here, and we made a correlation of this delta G as a function of the applied voltage in the sequence and the previous conductance. And it turns out that the response of the device really makes sense, and it shows a potentiation region for relatively large voltage, negative voltage, and relatively small initial conductance. So this means that conductance initially is zero. The traps are basically empty or at equilibrium. You apply negative voltage, this will result in more emptying of the traps, more detrapping, and an increase in the conductance. On the other hand, you see a depression region here in blue. This depression takes place at low voltage and large conductance. So in this case, you're not applying any voltage, and the conductance is pretty large, which means that there are many empty traps, and this will result in spontaneous trapping of electrons and decrease of the conductance. So this is also shown here. This is the delta G as a function of the pulse voltage. You can see this exponential behavior at relatively large voltages. And this is a very nice nonlinear function that can be used for processing this electrophysiological signal with the reservoir computing layer. So we made some real experiment taking this brain slice. So this is a brain slice from a rat where epilepsy was induced by some drugs. We were not in charge of this experiment, so I cannot give you more details, but this brain slice was put under MEA, the microelectrode array. We collected this signal here. You can see pretty clearly the seizure, the ictal seizure from the brain slice, and we submitted this signal to the reservoir layer, and this shows the response in real time. So whenever you see the seizure, this was amplified. Of course, we are in a microvolt or millivolt range for these signals from the MEA. This excited the device by several orders of magnitude. So this is a very good response, nonlinear response by the device. We also took the same signal but reversed the sign because we wanted to be sensitive to the shape not only of the negative side but also the positive side. So we reversed the amplification gain and we collected the response under the negatively amplified signal, and we also observed the same exponential or a strong response by our device. And then we plot the change of the current on the positive gain and the change of the current on the negative gain as shown here. And as you can see here, there is a very nice correlation, and this and you have the clusters. Okay, clusters marking the all different activities, including ictal, interictal, baseline, and so on. So we then apply some very simple machine learning tools like decision tree or KNN or a support vector machine, and we could see that this activity can be easily recognized and distinguish one from the other. Then we also made some in vitro experiments. These are some spheroids, similar to the brain slice, but this is something different. On the MEA, we took these signals and we also prepared a board with our devices connected to the oscilloscope and control PC, power supply, and everything else. Here you can see the signal. Signal was not as nice as before because of the environment was a little bit more noisy. And also the spheroids were not as efficient in giving this signal. And then we collected the signal from the negative gain, the positive gain. Then we put a simple seizure threshold, okay? So as soon as both the first signal, first output, and the second output exceed a certain threshold, we recognize a seizure basically simply based on a threshold. And here you can see the seizure signal is actually very nicely synchronized with the label here of the original signal, which means that actually this system is nicely working. Okay, so we made also a benchmarking of our system compared to other systems. And basically, I can tell you the very attractive feature here is the power per channel is very low compared to other approaches. The latency is also very, very attractive. Accuracy is also very nice. And basically, also the system is very simple. As you can see, with just one device, basically, or very few devices on a nanoscale, you can do a very complex processing of this signal. And here, this is Matteo Faronato, who is the first author of this work. Okay, conclusions. Now, basically, we have seen a couple of examples of devices, very simple devices, nanoscale, memristive devices that are capable of very advanced processing of devices and can be applied for replicating some neuromorphic functions like direction selectivity in the retina or tonotopic mapping of frequencies in the cochlea, and also reservoir computing of electrophysiological signal. So either mimicking the brain or probing the brain and trying to process the data and recognize and do some simple AI on the brain signals. Okay. Thank you very much for your attention.
Thank you very much, Daniele. Unfortunately, we don't have time for questions now, but there's a coffee break now, and I'm sure Daniele is here for discussing with you. We will meet again here at 11:30. Thank you.
Thank you.
But let's thank Daniele again.